let's say you're given a molecule to make a dot diagram. Now, a dot diagram is basically a model. It's a model of the molecule. It's a representation. So here we go. Here's a molecule, HCN. I don't know if I did this with you the other day, not this one, but one like it. First thing I do is I look at the molecule and I ask myself basically, what do I see? I look at the subscripts. I try to understand, am I looking at a molecule or an ionic compound? The fact that it's a weak acid, I'm going to go ahead, even though I recognize that it's two ions, they're going to be, it's more like a polar covalent molecule. There's no subscripts. So I'm going to go ahead and just draw this. Usually when you get a carbon-based compound, you can try among trying to build symmetrical molecules, among trying to put the least electronegative in the middle. You can also remember that carbon-based molecules are usually written in the order that they're bonded. And it is a molecule, so there has to be at least one bond between each element or each atom. So we do this. At the very least, that's what we're going to have. Now you can see that carbon is not happy. You know what? I'm going to do this up here because I'm going to use this room to do the calculations here. Let's do that here. HCN. You can see that carbon's not happy. It only has two bonds. Each bond is 2 electrons. So that means the carbon's only looking at 4 electrons. 2 for one bond, 2 for the other bond. That's 4 electrons. All the elements want to see 8 electrons. The only ones that actually see 8 on their own are what gases?
Noble gases?
The noble gases are the only elements that actually see 8 on their own. All other elements must form bonds to get 8. And so that's what they're doing. But with carbon only having the 2 bonds, it only sees 2 plus 2, 4. So it still needs to see 4 more electrons. And we're gonna see that those 4 more electrons come in the form of bonds. Now, this step-by-step procedure that I'm about to take you through, this is a verbal mathematical approach to what my menu approach does, except for this is a little better. It handles even more examples than my menu does, because if you've read the book, chapter 7 lets you know that there are even more complicated bonds than sp hybridized or sp blended bonding. So this is not a bad thing to learn. It's a good thing to learn. You don't always need it, but when you do need it, it's there. Solving chemistry problems and painting pictures, writing a book, fighting a fight, they all have something in common. The more tools in your toolbox, the more skills that you possess, the more likely your success. So this is a tool, so is the menu. Learn them both, and you'll have a better chance of success. So we've connected all the atoms with one bond, but we can see carbon's not happy. We can see nitrogen's not happy. Now notice hydrogen is happy. Hydrogen only needs to see 2 electrons because it only has sublevel S. Hydrogen on period 1 only has one sublevel, the first one, sublevel S, which holds 2 electrons. Remember, for every energy level you're at, that's how many sublevels you can see. That's why when we did the pyramid to make the electron configuration, row 1 had S, row 2 had SP, row 3 had SPD. Every energy level has that many sublevels. Energy level 1 only has sublevel S, which holds 2 electrons. Here we see hydrogen sees the 2 electrons of that bond, so it is happy. Carbon is not, nitrogen is not. So let's do this right here. How many total valence electrons are available in hydrogen cyanide? Well, hydrogen has 1 valence electron. Carbon has, how many valence electrons does carbon have?
4.
4, that's correct. Who was that?
Daniel.
Daniel, good job. How many valence electrons does nitrogen have?
5.
5, who's that?
Pilar.
Good job, Pilar. So we're going to total this. So we total it up and we see that we have a total of 10 valence electrons available. The next question is, what's the total valence electrons needed? Now we just said hydrogen needs 2. How many valence electrons does carbon want total or need total to be stable?
8.
8. I said earlier, all elements need 8 except for hydrogen and helium. So how many does nitrogen need to be stable?
8.
8. All right, so now we total up what we need. 8 plus 2 is 10, plus 8 is 18. So the total needed is 18 electrons. Now, the reason why elements bond is because what they have is not what they need. They have 10, they need 18 together, so they're going to end up sharing electrons. Well, how many electrons do we need to share? Whatever we don't have. So 18 minus 10 is 8 electrons in bonds. We got to have 8 electrons in bonds. That's this step right here. But bonds are 2 electrons each. So if we need 8 electrons in bonds, let's divide that by 2 per bond. And that'll tell us how many bonds. 4. Now look up there. We've got 2. We need 4. So we're going to add 2 more bonds. We cannot add bonds to hydrogen carbon because hydrogen can only have 1 bond. So the other 2 must go here. Now that works for carbon because that allows carbon to see 2, 4, 6, 8, which is what it wanted. Nitrogen's not happy right now. It sees 6, but it wants 8. Nitrogen also wants 8. So what happened? Well, remember we have 10 electrons and 2, 4, 6, 8 of them are in bonds. So if we have 10 electrons and 8 are in bonds, that means 2 of them are not, and we can put them right there. Now nitrogen sees 8, 2, 4, 6, 8, and all of our electrons are accounted for. Okay, now I'm gonna stop you here and introduce something that's down at the bottom of today's notes. Not all the way down, but about 2/3 of the way down. There's some notes that I wrote that I'm pretty proud of. They're good notes. They're a little complicated maybe, but they talk about how do you know the shape of a molecule? How do you know the geometry of a molecule? So I'm going to take a break from the dot diagrams, and I'm going to show you this alongside the dot diagrams at the same time. So let's take a look at HCN. We just drew this, HCN. What shape is this molecule? Well, if you looked at my class notes last class, there's drawings of things that look like turkeys. They're the SP, they're the S and the P sublevels of the atoms of electrons. As they fly towards each other before they collide, the orbitals end up getting bent backwards, which takes energy. The energy comes from the speed of the atoms. Now, as these atoms are flying towards each other, their sublevel electron orbitals get bent backwards, including the S sublevel. And the S sublevel gains energy first. As you bend it, it's like stretching a spring. It puts energy into it. And the S begins to approach the same energy as the P. And at some point, it achieves that. As it's bending back, stretching back, the S gets the same amount of energy as the P's. And the electrons are now free to rearrange in all of these new energy levels called sp orbitals. They're mixed together. The S has bent. The P's have bent. They equal each other in energy. So the electrons just blend them together. And now they're called, instead of calling them S or P orbitals, we call them sp orbitals. They look like baseball bats if you look at my notes. And there you can blend together the S with 1 P, which gives you 2, the math is simple. S plus P, 1 plus 1 equals 2. And you end up with 2 baseball bats. These are called sp orbitals. Okay, this would be sp1, this would be sp1. Why is it sp1? Because this is S and this is 1 P orbital. sp1. Now, if more than 1 P orbital blends together, that's the P, and here's another P. Remember, they look like propellers. So 1 plus 1, 1 plus 1 plus 1 equals 3. In other words, the S plus 1P plus 1P equals 3 SP, and we call it SP2. This is SP1, as I labeled it. We get 3 of them. 1, 2, 3. They look like little cartoon baseball bats. Those are just orbitals in which the electrons in bonding are going to, when they bond, they're going to be dwelling in those. They're going to be carving out those spaces. They're going to be occupying the space. Now remember, there's 3 P's. So if we add together the S plus all the P's, PY, PX, PZ, then that means that's PY, PX, PZ. That means 1 plus 1 plus 1 plus 1 equals 4. And this is a S plus 1P plus 1P plus 1P. So you get sp3. And there are 4 sp3s, and they look like baseball bats. Okay. This is all in my notes for the last 2 days. I hope you've been studying my notes. That was your instructions. Let's talk about what shapes these things make. So if you have 2 sp1s they will arrange themselves, since they hold electrons, they will arrange themselves in 180 degree separation to keep the electrons as far apart as possible. So it's going to look like this. That's 180 degrees. And just like the px and py orbitals, each sp can hold 2 electrons, spin up and spin down. Those are bonding electrons. I'm going to show you what that looks like in a minute. But notice that when you're in a straight line like that, it's a line. It's a line. And we call that linear. Line R, linear. It means they're in a straight line. If we have 3 sp2s, now notice s plus p2, s plus 2 is 3. You'll have 3 of these cartoon baseball bats. They will separate themselves in space in the shape of the Mercedes-Benz symbol. So you'll have one up, you'll have one over here, and you'll have one like that. It looks like a Mercedes-Benz symbol or maybe a tri-blade propeller. Okay, and again, you can have 1, 2, 3, 4, 5, 6 electrons. I'm not going to show that. We call this trigonal, which is a fancy name for triangle, trigonal, and then planar means flat. So notice, sp1 is linear, sp2 is a triangle. Now, if we blend all of the if we blend the s plus all of the p orbitals, we get 4 sp3 orbitals. 1, 2, 3, 4. Now you would think that they would form a cross and be 90 degrees separate. But that's not what happens, because that's flat. And atoms don't have to be flat. Now, all groups of 3 like that are always flat. They are. You can't make them not flat. Try it. That's why real, authentic, antique stools only have 3 legs, because they can always find a plane. They can always find a flat plane to stick to. If you go to a restaurant, you sit on a chair or a table with 4 legs and the floor is not smooth, your table or your chair wobbles and it drives you crazy. You put napkins or something underneath it. But if you had a 3-legged stool or a 3-legged table, that would never happen, because you can always find a flat plane for 3 points to lie on. 3 points like that are flat. That's why it's called planar. But that's not the case with 4. What you can actually do is bend this one up out of the plane, and you can bend that one down into the plane. And when you do that, you get something called a tetrahedron. It looks like a music stand. And you can put your music up here and stand there and read your music. No, not really. That's too small for that. But what does that look like when you do it with the sp orbitals? It looks like this. It almost looks like that one, but you got that other leg back there. Here's what that looks like. I got a little model here for you. That's the music stand. That's sp3 right there. They call it tetrahedral. Tetra for 4. I'm not sure what hedral means. I looked it up. Guys, you need to memorize that sp1 is linear, sp2 is trigonal planar, and sp3 is tetrahedral. You need to memorize that for the exam. That is the end of chapter 7. Now, knowing that, I'm going to show you how to look at a molecule and determine what shape it is in. I'll put over here, sp1 is linear, sp2 is trigonal planar or triangular. Trigonal is like polygon, polygonal. It's just a fancy way of saying triangle. Planar. Planar means flat. And sp3 is tetrahedral. Now here's how you're going to determine the shape. Quick and dirty, right here. Count the sides of the central atom that has electron, either bonded or unbonded. Count the sides of the central atom that has electrons. The sp hybridization that equals this gives the shape. Let me explain that. So let's say we have a central atom X. I'll do this. Example. If we have X like this or like this, both of these, or this even, let's do this. all three of these have electrons on only two sides, left and right, left and right, left and right. So SP1, why? Because S plus 1P equals 2, and that is that number. This is SP1. So what does that tell you? It tells you that this molecule is going to be a straight line molecule. It's not going to be bent. It's not going to be pyramidal. It's not going to be triangular. It's going to be a straight line. This is an example of a linear molecule. This is 2 carbons, 2 hydrogens, C2H2. And if you do the dot diagram for it, you get a triple bond and a single bond. So that's 2 sides of this carbon have electrons. That means this is linear. And then you look at this carbon and you see left and right have electrons. So that means this carbon is linear with this one. So this whole thing from here to here is one straight line. If you look at it down the axis, you know, it's a straight line. Now let's look at another example. Let's look at another example. What about if we have, oh, I'm going to do SP1, is linear. I'll rewrite this again. SP2 is trigonal planar. And SP3 is tetrahedral. So let's look at another one. Let's look at this. We have X with a double bond and a single bond and a single bond, or if we have X with a double bond, a pair of electrons unbonded, and a single bond, or maybe we have X with a pair of electrons and a double bond. Is there another way of doing this? I don't think so. All right. Notice this has 3 sides. Left, right, bottom, left, right, bottom, left, right, top. This one's left, right, top. This one's left, right, bottom. So is this one. So that one's here and that one here. These are 3 sides. So that means SP2 because 1 plus 2 is 3. That tells you that these molecules are going to be trigonal planar. Let me show you trigonal planar. So here you see a trigonal planar. That's the Mercedes-Benz right there. This carbon has electrons 1, 2, 3 places, so they're going to be trigonal planar. And that angle of this angle is 120. I forgot to mention the different angles. So let me write down the different angles. SP1 linear is 180 degrees separation. Trigonal planar is 120 degrees. And tetrahedral, you think it's 90, but it's not because they can bend out of the plane. 109.5. You're going to need to learn those angles. All right. Last one. Let's say we have an atom that's bonded like this, or an atom that's bonded like this. Nope, hold on. Maybe we have this one, or maybe we have this one, or maybe we have this one. In all cases, all of these have 4 sides of electrons. Whether they're bonded or unbonded, left, right, top, and bottom. So that means 4 sides means SP3. 3 plus 1 is 4. So that means it's not SP1. It's not linear. It's not SP2, which is trigonal planar. 120 degree separation. You're looking at SP3, which is tetrahedral at 109.5 degrees. Let me get rid of that. That's 109.5 degrees. And that means you're going to have atoms that look like this. Central atoms that look like a music stand. Okay, that's that one. So let's look at HCN. And then we're going to go back to your problems. HCN, we've already decided, is HCN. Hydrogen cannot hybridize. To hybridize means you blend two things together. A Prius is a hybrid car. It blends a gas engine with an electric engine. A Tesla is not a hybrid. A Tesla is an electric car only, not a hybrid. Only has the S sublevel. Now carbon. How many sides do you see electrons on carbon?
Two.
Besides.
Two sides. You see electrons on the left, you see electrons on the right. Two sides, and that means that this is sp1 hybridized. Over here, what about the nitrogen? How many sides do you see electrons on nitrogen?
Besides.
How many?
Two.
Two, left and right, same thing. So that means from here to here is a straight line, and from here to here is a straight line, which means the entire thing is a straight line. So this entire molecule is linear. It makes a straight line. It's a lot like this. If you can imagine, if this maybe were, red or blue or something, then you would have your hydrogen, your carbon, your nitrogen, and instead of a ball there being another hydrogen, you would do this. I'll show you what it would look like. In models, they just stick out there like that. There's no ball on that end. That represents, that's like that. It's a straight line. I gave you a lecture, I don't know, was it last week when I talked about the atoms that were flying towards each other with their virgin s and p orbitals, and individual atoms, their s and p, x, p, y, p, z orbitals are going to be intact, populated with electrons, but they're not happy. They're very low energy. They're very high energy, very low stability. And if they come into contact with anything else, everything's made of atoms. When they come into contact with other atoms, well, they're all moving. Those that are in solids are vibrating. Those that are in liquids and gases are whizzing around. Of course, the ones in liquids are colliding more often. They're all moving. And so when one atom comes into contact with another atom, the orbitals are going to get bent backwards. The kinetic energy of the motion gets bled or tapped, taken away. It gets transferred from the movement of the entire atom to the movement of the orbitals. The orbitals actually bend backwards away from the approaching atom because the electrons don't like each other. Now, that doesn't mean the nuclei don't like each other's electrons. They need each other's electrons, but the electrons themselves don't like each other until they collide, or at least come close enough so that the repulsion forces make it feel like they collide. And then, of course, momentum makes the bent, stretched s and p orbitals. The s orbital has gained energy, potential energy, so that the electrons in the s and the electrons in the p are now free to flow between the s and the p. They make what we call sp hybridized orbitals. They slop over and overlap each other. Now, when they do that, what's that?
I was going to say they create a bond.
They create a bond. If that overlapping of sp hybridized orbitals has one electron here and one electron here, and it makes both nuclei happier or lower in energy. What do they call that? Personification, right? When you give human attributes to an inhuman object, that's personification. So yeah, it's terrible when we personify things. It really takes the science out of it. But when you're first learning something, it helps. It's all about the energy. If it reduces the potential energy of the system, it's going to work. It's going to form the bond. So when you have overlapping sp hybridized orbitals, they will remain hybridized and form what we call a single bond, sigma bond. Sigma, the Greek letter sigma. It's in chapter 7. You'll want to look at that, or you just Google what's a sigma bond.
It's like the E basically, right? It's the same.
Sigma looks like an O with a curly Q at top. Oh, you're thinking about capital sigma. I'm talking about, this is lowercase. We say sigma.
Wait, so a sigma is the same thing as a sigma bond?
Well, sigma is when two overlapped sp hybridized orbitals form a straight line between the nuclei. It forms a sigma bond. It's kind of like related to the s orbital, I guess. But a single bond is a sigma bond, and a sigma bond is the basis for all bonds. It turns out that double and triple bonds are actually based on a sigma bond first, and then the unhybridized p orbitals make what we call pi bonds. I don't know if that's in my notes, but it's certainly going to be in chapter 7. If you look at chapter 7, I don't think I'm going to go too far into that on the exam, because I don't go too far into that in the lecture. I'm just telling you right now, when the collision occurs between two atoms, it's like an accident. You've got your Coke sitting there, and you hit something, the Coke's going to slosh forward. Well, it's called momentum. That's what the electron clouds do, the electron orbitals. They slosh forward. The ones that overlap and provide the ability for both nuclei to see the needed electrons to become stable. They're going to remain. If there are sp hybridized orbitals that don't do anything for that atom, they're going to spring back to being unhybridized p orbitals. You know, the px, the py, pz. Only the ones that actually overlap and produce sharing of electrons that lowers the energy of both nuclei are going to stick. The other ones are going to remain or revert back to being unhybridized p orbitals, because the motion will basically stop and they'll spring back into whatever they were. Now those unhybridized p orbitals, if they're parallel, which I say parallel p orbitals on adjacent nuclei, those are the basis for the second or third bond that make up a double or triple bond. You've got the sp. So if you want to think of it this way, and I didn't teach anybody else this year, you got a triple bond in carbon-carbon. You could always say this is sigma, and this is pi, and this is pi. Okay, all bonds contain a sigma bond. All bonds contain the overlap sp hybridized. When I say all, I'm talking about covalent. We're talking about covalent. All covalent bonds, single, double, and triple bonds, possess one sigma bond, the overlap sp.
And they have more than one?
No, you can only have one sigma bond, one and only one sigma bond. Any additional bonding, such as in a double bond, since you got to have one sigma, the other one is going to be pi. Now, I'm not going to, there's probably not going to be a whole lot of this on the test because I just don't have time. But where those pi bonds come from, if you've got a carbon and a carbon with the overlap sp like this, well, then you're going to have unhybridized p sometimes. And what they end up doing is bridging. So that would be a double bond. I think that's in my notes. If it's not in my notes, this is sigma, this is pi. Now the pi is actually a complete loop like that. And that would be a double bond. If you happen to have an unhybridized p coming out of the screen at you, let me make it a different color than you can see it. If you got an unhybridized p coming out of the screen at you, that's where you get your triple bond. The pi bond, that's another pi bond. The pi bond is a loop. It's a circuit that the electrons fly around in. Melanie, what I'm sharing right now is not going to be on the test, but some people were asking questions. I was simply trying to state that sp hybridized bonding orbitals come from colliding atoms where they, as they get closer and closer, the s sublevel transfers kinetic energy into potential energy. The atoms are slowing down. The energy is going into stretching the s from being spherical into being, you know, a long bat-like shaped orbital where the electrons are really stretching farther and farther away from the approaching atoms. At some point, the s electron is going to have gained enough energy so that it will be close to the p electron energies, and then they're indistinguishable. So the orbitals become indistinguishable. They become a new orbital called sp hybridized orbitals. The ones that persist after the collision because they provide a route for shared electrons to be shared by two nuclei and thus lower the energy of the two nuclei, those will persist. The ones that are not are going to spring back as, well, there's two things. They will either spring back as unhybridized p, or it's possible if there are other atoms in the vicinity colliding, they may end up springing back and then suddenly finding that they're overlapping somebody else's orbital, and then they convert to sp hybridized orbitals with that. So you could, it's not common that you have a multi-car collision. You know, if you go out here and watch the intersection and you take statistics on car accidents, it's very rare that you get 3 cars collide at the same instant. Usually it's one car collides with another car, and then maybe later another car hits that. But it's very rare that 2 cars hit one car simultaneously. But it can happen. It can happen. And the same thing can happen in the atomic world. It is possible that 3 atoms collide at the same time. And you'll see if you go into higher level chemistry, when you start doing statistics and kinetics, the speed or rate at which reactions occur, you'll see that one-on-one collisions occur much more commonly than if a reaction requires, 3 atoms to collide simultaneously. It's a very slow reaction. It's very rare, very rare. Okay.
Mr. So in like carbon tetrahydride, like CH4, those bonds between each carbon and hydrogen wouldn't be all sigma bonds?
Yes, they are. They are.
So that one has 4 sigma bonds?
Yeah, carbon tetrachloride, methane, any carbon CX4 is going to have 4 sigma bonds. Now, they don't necessarily have to happen. They don't have to happen at the same time. You can make carbon tetrachloride 1 chlorine accident at a time. So you could start with methane. And you could collide chlorines with methane, and it could occur 1 chlorine at a time. So maybe initially you get methyl chloride, and then you get methyl dichloride, and then you get methyl trichloride, and then you get carbon tetrachloride. Okay, so I don't know what the synthesis process is for making carbon tetrachloride. I know we do. It's made in factories. A chemical engineer designs those factories. That's what chemical engineers do. They design the large scale reaction vessels that produce, synthetic oil, drugs, and whatever we're making nowadays, our polyester clothing, all of our synthetic fibers are made by by factories that use chemistry designed in reactor systems by chemical engineers. And so there is a process for making carbon tetrachloride, and there are 4 sigma bonds. They did not occur all at the same time. That would be nearly impossible. That's like playing the lotto and getting all 5 numbers or all 6 numbers simultaneously, right? It doesn't happen often. And getting 4 chlorines to collide with the same carbon simultaneously is like winning the lotto. It's just very rare to happen.
So is that like an exception to what you said about all bonds possess 1 sigma bond?
No, that's not. We're misunderstanding each other. When I say all bonds contain 1 sigma bond, I'm talking about bonds. So a single bond is a sigma bond. A double bond consists of 1 sigma bond and 1 pi bond. A triple bond consists of 1 sigma bond and 2 pi bonds. And that's all there is.
Oh, because these are like different bonds happening in
Yeah.
Oh.
So if you look up here at the top left of the screen, you see, let's say this is carbon, and it's got a sigma bond to the left. We know that has to be a sigma bond. It's got a triple bond to the right. One of those of the triple bond, 1 is sigma, the other 2 are pi bonds. So that's what I mean when I say every bond consists of 1 and only 1 sigma bond. Any additional bonds are pi bonds. Now, what you're talking about and what I'm talking about are 2 different things. You're talking about, I'm talking about in any bond, 1 is a sigma. You're talking about an atom. You're saying a carbon has 4 bonds and there's 4 sigma bonds. Yes, that's 4 bonds. Here, a triple bond, that's 1 bonding side. Of that triple bond, 1 of them is sigma, the other 2 are pi.
Oh, okay, yeah, I was confused. Thank you.
Okay. All right, now let's get away from that. Let's get to geometry because that's really what I'm trying to do. I really didn't even go into the sigma pi stuff with other students. And so the only part of that will be on the test will be concepts that you should have gleaned from reading. I'm not going to have you doing heavy duty, concept stuff about sigma and pi because I didn't go over it with any other students. All right, here we go. These you will recognize from my periodic table of bonding. How do the carbon family, every element in the carbon family makes 4 bonds. How did the nitrogen family bond? Every nitrogen family element bonds with 3 bonds and 1 unbonded pair of electrons. How did the oxygen family elements bond? Well, they bond with 2 bonds and they have 2 unbonded pairs of electrons. How do the halogens bond? They bond with 1 bond and have 3 pairs of unbonded electrons. Now, I've taken those bonds and I've organized them by thinking about how many sides of the atom you would actually see electrons on. Now, when we learned about atomic dot diagrams, and I made a big stink over the book is wrong, Beethoven's right, because I use Altball and Hund's rule. One of the things I pointed out is that there are 4 sides of an imaginary box around the element because there are 4 orbitals, the S, the PX, the PY, and the PZ. And you put the 2 in the S, and you put 1 in the PX, 1 in the PY, 1 in the PZ. Then you come back, Hund's rule, and start pairing them up. Well, it turns out that since the math describing how many hybrid orbitals you get is very simple, it's simple addition, that you end up with a maximum at this stage, in this class, we're not going to talk about it anymore other than I'm going to tell you that there are more. You end up with a maximum of 4 hybrid orbitals as well, because the math is simple. You get as many hybrid orbitals out of hybridization as what you put in. Arturo, if you're on your phone, please put it away. You get out of a hybridization event as many hybrid orbitals as the number of unhybridized orbitals put in. So if you add 1 S and 1 P, you get 2 sp hybridized orbitals out. If you add 1 S, and that's all you have, by the way, you only have 1 valence s orbital. If you add the s orbital to 2 of the p orbitals, you get 3 sp orbitals out. If you add the s orbital to the 3p orbitals, you get 4 sp orbitals out. And so since you get a maximum of 4, you can likewise imagine the bonded atom inside an imaginary box with 4 sides. And instead of calling 1 the S and 1 the PX and 1 the PY and PZ, well, all 4 sides are equal sp orbitals. And I'm just going to refer to them as top, bottom, left, right. And so what I'm doing is I'm trying to prime you. I'm trying to prep you to be able to determine the geometry. And you do that step 1 by drawing the dot diagram. Step 2, look at the central atom. The central atom is the less electronegative one around which the other atoms are generally organized. Look at that central atom and ask yourself, how many sides of that atom do I see electrons bonded or not? And so here we see on say a carbon that makes a single and a triple bond, we see that there are 2 sides with electrons, left and right. It could be top and bottom, it could be left and bottom, doesn't matter. We also see that that same carbon could do two double bonds. And it's not just carbon. X means any element that bonds like this. It's still two sides, a double and a double. Here we see this would be like a nitrogen or a phosphorus. It makes a triple bond to the right, and it has an unbonded pair of electrons to the left. It's still two sides. Bonded and unbonded electrons still count. So left, right, two sides. So here's how you interpret that. When you realize that the element has electrons on two sides, you understand that W/E means with electrons. Two sides with electrons equals the number of orbitals that you added. In other words, the number of sides with electrons has to equal the number of orbitals hybridized. So you always blend an S with some P. So if you have a total of 2, then you had to go 1 plus 1, S plus 1P. So because you're only adding 1P, we call this hybridization SP1. I don't know why we don't call it S1P, but it's called SP1. S plus 1P is SP1. And remember, you get out as many as you put in. So if we put in 2, the S and the 1P, that's 1 plus 1, you're going to get 2 SP1s out, and they're going to spread apart as far as possible. Whenever, what was that? There was some T-pose Thursday or T-pose Tuesday. Remember that way back in the day? No? When I used to do this, people go, they talk about T-pose, whatever. You get the 2 SP1 orbitals, they want to spread apart as far as possible. I'm the nucleus. These are my 2 SP hybridized orbitals. They're going to be 180 degrees separate, okay? And you can see I wrote right here 180 degrees separation. Moving on. Oh, because they're 180 degrees, let's look at a model. Here you go. Here is C2H2. And if we look at that carbon, obviously you can't have one central atom. They're 2 identical central atoms. So let's just look at this one first. And by the way, you can analyze small molecules by looking at the central atom, and you can get a simple geometric shape out of that. But you can also do it for more complicated molecules. And the way you do that is you look at one and then you look at the other, and then you imagine how the 2 geometries fit together. You can end up making a ring, you know, and if you go into biochemistry, if you go into biochemical research, maybe you want to go into protein synthesis, or you want to study, you know, vaccines or viruses, or maybe you want to study Crutchfield-Jacobson disease, the mad cow disease of humans. That's a very interesting disease. That's where you go crazy in your brain, from your proteins of your brain unfolding from one geometric shape and folding into another one. And then you lose functionality of your brain tissue, obviously. And so that has to do with the geometry. But you got to start with molecular geometry to understand tissue geometry. Because tissue, there's actually, I believe they call it primary, secondary, and tertiary geometry. Primary geometry is the geometry of the individual molecule. And then you imagine, as you link, you know, longer molecules together, that's called polymers. Polysaccharide would be one example. Multiple sugars. As you link these molecules together, they end up interacting with each other through something called hydrogen bonding. I hope they taught you that in biology, because we didn't talk about it. It's where the hydrogen, obviously hydrogen bonding, the hydrogen sticking out from one molecule is attracted generally to an oxygen or a nitrogen or a sulfur on another one. Okay, and they cause the molecule to start bending. And in proteins, like, there's not much of a difference. This is going to gross you out maybe. But there's not much of a difference between snot and hair. If you look at the ingredients that go into hair and the ingredients that go into snot, it's about the same thing. The only difference is the order of the amino acids. Because what happens is when you put enough little molecules together, and each molecule has a little bit of a bend or a shape to it, the next one has to be bent according to that angle, but it has its own angle for the next one, and they end up bending back on themselves. And eventually, if you have enough linked together, they bend back to themselves, and then the hydrogen here and then the nitrogen or sulfur or oxygen there attract, and they close it, and that's called like a tertiary geometry. And depending on where that hydrogen and that oxygen or nitrogen is, it's going to make the difference between something sticky, gooey like mucus, or, you know, curly hair or something. And what happens with Jacobson-Crutchfield or Crutchfield-Jacobson is there, I believe it's a virus or a viral particle gets into your bloodstream, and it causes your brain proteins to disengage and then re-engage a different way. So obviously it's doing something to one of the molecular geometries. Maybe it's breaking a bond or something, who knows, but it's changing the geometry of 1 or 2, you know, molecules in that whole long protein chain, and that causes it to refold and become non-functional, and you go cuckoo. So that's, you know, that's interesting research, and it has to do with molecular geometry. So here we are again. What happens when you have, you know, a carbon with a double bond and a single bond and a single bond? Well, we would say that has 3 sides, and so, you know, left, right, bottom, or it could be left, top, you know, right, or it could be, you know, top, bottom, left, or top, bottom, right. It doesn't matter. 3 sides, and those 3 sides, by the way, sigma, 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 pi, right? Remember, every one of these bonds has to have at least one sigma, one and only one sigma, 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 pi. The one in a double bond, the second bond has to be pi. In a triple bond, the other 2 bonds have to be pi. But here we go. these three regions are going to want to splay out as far away from each other as possible. So you get the 120-degree separation. You get a 120-degree separation. We call it trigonal planar. Trigonal is a weird name for triangle. Planar means flat. And here's an example. This is C2H4. C2H4, you can see that top carbon with its double bond to this carbon, and it's, it's two hydrogens. It's going to be 120-degree separation. 120, 120, 120. And it's planar because it's flat. You'll notice the way it has to bond, the whole thing ends up being flat. So there you go, trigonal planar. Now, something we did not talk about, but I need to throw in, this does matter. For every unbonded pair of electrons, the other bonds get reduced by 2.5 degrees, and I'll explain why. These things are spreading out to get away from each other because the electrons in each bond repel the other electrons. Each region repel the other region. So that's why you end up with a symmetrical 120, 120, 120 separation. But think of it this way. The electrons are repelling each other because they're negative, but the electrons in a bond are not as negative as the electrons that are not in a bond. Because the electrons that are in a bond are connected to some protons called the nucleus. So the protons of the nucleus that they're bonded to kind of neutralizes the negativity of the bond, which means bonded electrons are not as strong as unbonded. The unbonded electrons push stronger, and that ends up closing the angle a little bit. And it turns out that it closes it, write this down, one unbonded pair of electrons will close the other angles by 2.5 degrees. And it's 2.5 degrees per pair. So if we look over, we'll look over here, because this doesn't really count.
Wait, mister, can you repeat that?
Yeah, for every pair of unbonded electrons, it closes the bond angle of the others by 2.5 degrees. For every pair of unbonded electrons, it closes the bond angle of the other bonded electrons by 2.5 degrees. So if you have one pair of electrons, it makes the bond angle of the bonded electrons 2.5 degrees less than what you predicted based on the geometry. If you have two pairs, then it's 5 degrees less. If you have three pairs, there's really no other bond angle, because if you have three pairs of unbonded electrons, then you only have one other side with electrons, and that's going to be, it has nothing to measure an angle from. You can measure the angle from the unbonded electrons, but that doesn't really, it doesn't count for shape. I'll explain a little bit more later. All right. What else do I have here? Okay, that would be sp2. sp2 hybridization. You can look at it like this: three sides, s plus two p's, sp2. You can also go s, p1, p2. All right, sp2 hybridization based on trigonal planar, 120-degree separation. The actual bond angle is going to be determined by how many unbonded pairs of electrons there are. Now we go to four sides. So here you have your methane, CH4, or your carbon tetrachloride. Carbon in the middle, 4 bonds. Now you would think, if you got two things separated by maximum separation, you get 180. Well, that's 360 divided by 2, so it's 180. Yeah. Then you go to 3 and you say, well, 120. That's 360 divided by 3, so that's 120. Yeah, great. How come it's not 90 when you go to 4? Well, that's because the 360 divided by 2 and the 360 divided by 3 works, because you can put 2 things and 3 things on any plane. And you can put these 2 things fit on a plane. So you can talk about planar geometry 360 degrees. You can put 3 things bonded on a plane, and they don't have any other option. You say, what if I bend it that way? Then the plane is this way. The plane is this way. There's always going to be a plane for 2 items or 3 items, but that's not the case for 4. If you want maximum separation for 4 bonds, remember, you can actually bend one of them off the plane that the other 3 or 2 are on. You can do that. You say, I want to get further away from you guys. So you bend it up a little bit, and that gets them a little further away from those guys. And if you bend the second one down, bend one up and bend one down, you actually increase the bond separation from 90 degrees to 109.5. And that's what this is. Here's your methane or your carbon tetrachloride right here. It's not a cross. That looks like a cross. It's not a cross. It's a tetrahedron. And the angle is 109.5, because if you look at these two as though these two in that center are the plane, what we've done is we've raised this one up and we pushed that one down. And that gives everybody a little more separation. It lowers the potential energy of that system. All right, we call that shape a tetrahedron. The bond angle is 109.5. But that same thing works here. For every pair of unshared electrons, it reduces the bond angles of the others by 2.5 degrees. So methane would be that. 4 hydrogens, 4 bonds, 1 carbon. Ammonia, NH3, ammonia would look like this. NH3, but these electrons are not as neutralized as these electrons by the proton here. So they actually push down. They actually bend these other guys down more, so that this angle is reduced by 2.5 degrees down here. And we then see that that's 107. And that's why the angle on ammonia is 107.
Wait, but wouldn't NH3 be a 3-side trigonal planar?
Nope, because look, the electrons on top matter. So one side, top, bottom, left, right. That's 4 sides, sp3. sp3 means it's going to have tetrahedral electron structure, but in terms of the geometry of the molecule, you're not going to see the electron pair. They're a trillion times smaller. I don't know what the actual number is, but the electron pair is like a trillion times smaller than a hydrogen atom. So you don't see those the way you would see the hydrogens here. So actually, NH3 is not a tetrahedron. The angles are tetrahedral, but you don't see the top. So it looks more like a shallow pyramid. And so that's what it's called. It's called a trigonal pyramid. You know, it's a triangle pyramid, triangle base pyramid.
If there's like 3 or 4 sides, but there's only one side that has bonds, is that linear?
Yes, it would have to be, because when you talk about the bond angles, you're measuring the angle from one bond to another. So if you only have one side with a bond on it, there's nothing to measure it against. So it's linear.
But what would the angle for that one be? 180 still?
Well, the angle between the electrons is not 180. It's still going to be approximately, on the tetrahedral, still going to be approximately 100 and some degrees, between the electrons. But the shape of the molecule is going to look like a straight line, because you're going to have two objects. You're not going to see the electrons. You're just going to have two objects with an electron cloud between them. That's going to be a triple bond or a single bond or whatever it is. And what's the shortest distance between 2 points? A line. In geometry, in planar geometry, it's a line. It's not true on a globe, by the way, right? On a sphere, the shortest distance between 2 points on a sphere is called the Great Circle. You draw a curve towards the poles, and it's actually shorter than going equatorial or circumference. I don't know. You can check it out. That's because curved space geometry is very different from what we call Euclidean geometry, which is the geometry of flat space. So when they tell you, that a triangle can't have two 90-degree angles in it, that's flat geometry. It's not curved geometry. You can, on a globe, you can have two 90-degree angles on the surface of the globe for a triangle. Go check it out. Think about it. All right, moving on. Let's talk about this one. Mira, here we have some element with 2 bonds and 2 pairs of unbonded electrons. So it's going to be tetrahedral in its electron structure, but think about it. 2.5 degrees, 2.5 degrees, a total of 5 degrees. So the bond angle is 104.5. And if you look at it, it's not going to look. Let me see if I can do this. I can't really. Yeah, I can. If I'm covering up one of the hydrogens. So you'll see this one, and you'll see the center one. You do not see this, you do not see this. That's why they call this bent. It's tetrahedral geometry. The angles are related to the tetrahedron. But what you see with your scanning tunneling electron microscope, you don't see a tetrahedron. You see a bent shape. Okay? So we call
Does that rule about the angle being decreased by 2.5 only apply to the 4 sides or to everyone?
All right. So it applies to both the 3 sides and the 4 sides where you have 2 sides that are bonded or more. Two or more sides that are bonded where you have the presence of one unbonded pair, you're going to decrease the bonding angle of the 2 bonded sides.
So it wouldn't apply to the last ones that are linear?
No, linear, again, we're talking about the bond angle between 2 adjacent bonds being decreased. So if you're linear, there's nothing else to measure against. Linear is always going to be 180. Or it wouldn't be linear. Okay, let's try something. Let's try this. We're going to do two quick examples. Draw the dot diagram for CH2O, and then we'll do another one, H2O. And here's what I want you to do. For both of these, I want you to do number 1, draw. Number 2, count sides with electrons. Count the sides with the electrons. 3, determine hybridization. What does that mean? It means tell me if it's sp1, sp2, or sp3. Determine hybridization. sp1, sp2, or sp3. Again, in this class, we're only going to do sp3. When you go to college, or if you take AP chemistry, you'll learn that you can also hybridize d orbitals, and that's where sulfate, SO4, 2 negative, and phosphate, PO4, 3 negative, can be described. And there are many other larger covalent molecules that end up being possible because the d orbitals hybridize as well. Number 4 is ID the geometry. The geometry. Obviously, I hope you all see that you cannot have H in between. All right, H is the one-armed Red Rover player. He cannot go in the middle. So H is going to go at least on this side, And how do you want to do it? You want to try symmetry? I don't know. That's not really symmetrical, nor is it really possible if you look at it. Because look, connect them all with one bond because it's a molecule, and then go from there. How do I make carbon happy? It's got to see 4 bonds. Well, the only way to do that is like that. That's not going to make oxygen happy. That doesn't work. So is there another way to make it symmetrical? Yeah, you could try this. Connect everything with a bond. Boom. How do I make carbon happy? Add another bond there. Oxygen wants that. Hey, that works. Show, man. That's acetone. Fingernail polish remover. Actually, they don't sell that anymore because it was linked to cancer. But there you go. Now let's talk about this. Let me clean this up here. I just wanted to show you. You can do this trial and error. If you do the menu, or if you do that,
Isn't that carbonated water?
no. Carbonated water is this. You got a CO2, which looks like this. And that, by the way, is why there's no liquid carbon dioxide. That's why they call it dry ice. The difference when we do water versus carbon dioxide, you'll see there's a geometric difference that makes life possible on Earth. Because water has a liquid phase on Earth, carbon dioxide doesn't. So, and that's because it's not a sticky molecule. It's complete. This side is negative, that side is negative. It balances itself out. So when you add this to H2O, then you get carbonated water. You get H2CO3. It adds up, and then this hydrogen pops off. One of those hydrogens pops off, which is what gives it that sour taste. Which then you add a bunch of sugar to and call it cola. And that cola, the sugar combined with the fizz and the hydrogen that pops off there, makes it it gives you that dual taste, the sweet and sour kind of taste. It makes it pleasurable. When it goes flat and all the carbon dioxide goes out and you're just left with water and sugar, it's boring. It's like, ugh. Maybe when you're 3, you drink that, but not now, right? You want something with a little kick to it. All right, let's go back to CHO, acetone. All right, back to acetone. What's the hybridization on that carbon? I mean, how many sides of that carbon has electrons on it? 3. Top, bottom, right. 3 sides, top. Does anybody need help with that? It doesn't have to be, top, bottom, right. It could be left, right, top. We could rotate this all around. It doesn't matter. But it's 3 sides, however you rotate it. And that means it's sp2. 2 plus that one is 3. Now, if it's sp2, it's trigonal planar. Now, trick question on the exam. What's the hybridization on hydrogen? What's the difference between a Prius and a Tesla? Speed. Acceleration. But really, one's a hybrid, one's not. The Prius is a hybrid, the Tesla is not. Prius has a gas engine, little one, like we need a motor. The Prius has a gas engine and an electric engine. Tesla only has the electric motor. Tesla is not a hybrid. In order to be a hybrid, you have to have 2 or more things blended together. Hydrogen only has s orbitals. Hydrogen does not hybridize. What ends up happening with this bond from hydrogen to carbon? The hydrogen's s orbital overlaps the carbon's sp orbital, and it works. Okay. Trick question. There's no hybridization on hydrogen. What about oxygen? What's its hybridization? How many sides have electrons?
1.
How many sides of that oxygen have electrons? Somebody on camera yell it out.
3.
3. We got left. We got top. We got bottom. They're not bonded, but all electrons' lives matter. Come on, guys, get with it. 3 sides. I could lose my job for saying that, right? Professors have lost their job for saying something like that. All right. 3 sides. So what's its hybridization? sp2. What's its shape, though? Its shape is different from its hybridization. You don't see what?
It's linear.
You're right. The oxygen makes a straight line to the carbon, because you don't see these. Well, let's do water. Do water.
Wait, so for that answer, we'd say that it's trigonal.
Yeah, the molecule. No. The molecule as a whole is trigonal planar because carbon is the central atom and it is trigonal planar. And if there were more things that added onto the oxygen, if this were a single, it couldn't be. But if we had something else bonded over here, then you end up with a more complicated, larger molecule. And you could say this one's trigonal planar, this one's bent, or something like that. Obviously, oxygen is in the middle. Hydrogen cannot be. You can't bond a hydrogen to a hydrogen. So this is what you got, right? Please say yes.
Yes.
What's the central atom?
Oxygen.
I know, but what's it? How many sides?
2.
4 sides. Left, right, top, bottom. All electrons matter. All right, 4 sides.
So it's sp3.
It's sp3 for the electron geometry. What about the shape of the molecule?
SB1.
Tetrahedral.
So no, it's not going to be. It's not going to be tetrahedral shaped molecule. The electrons are arranged. The electrons are arranged tetrahedral. But look what you got. You got those 2 hydrogens, and then you got a pair of electrons over here and a pair of electrons over here. You don't see those. You don't see them. So you end up with a bent shape. It's a bent shaped molecule, and that's why there's life on Earth. Because these are slightly positive, these are negative. So it makes like a bar magnet with the, if you put an arrow pointing towards the negative that way, and that makes them all stick together so we can have a liquid ocean. We can have liquid in our blood.
So all of the electrons, all of the molecules that have the unbonded ones that make the angles drop, are those all going to be bent?
Well, if you have one unbonded pair, you're going to be pyramidal. Remember, let's go back. The NH3 right here is a pyramid, trigonal pyramidal, I think it is. That's your pyramid. Now, if you have 2 unshared pairs of electrons, that's where you get your bent from, because you don't see just the electrons by themselves.
So the only time we can call something like trigonal or tetra is if each side of like 3 sides or 4 sides has like bonds.
Only time you can call something trigonal.
Like for the 3 sides, the only time we can call it trigonal is when there's no unbonded pairs.
Right. It's only going to be trigonal. The geometry of the molecule is only going to be trigonal when all of them are bonds. You remove a bond and replace it with unbonded, you get bent. Remove 2 and you get linear. Over here with 4 sides, 4 bonds, tetrahedral. 3 bonds, you're going to be pyramidal. 2 bonds, you're going to be bent. 1 bond, you're going to be linear. All right. That is all I have time for on this. I am now going to take you to something called balancing. And again, I want you to jot down. Now, I put some really good notes at the bottom of today's notes. They were also there last class. And there's a video link to a lecture I gave on this using a PowerPoint a couple years ago. And if you watch the video, it starts off with going through different ways that different people balance equations. Some people are artistic. Some people are quantitative like accountants. And some people are algebraic like me. I'm algebraic. So the technique I'm going to show you is a little bit algebraic. What you start with must equal what you end up with. That's the concept behind balancing chemical equations. In a chemical equation, the arrow, which we interpret as yields or produces or makes, we interpret that as a divider between what was there before called reactants and what is there afterwards called products. And obviously, you don't want to have the same molecules before and after, or nothing has changed. But you do want to have the same amount of mass, which means the same, and it doesn't mean, but the same kind and number of atoms before and after. So the same number of hydrogens before and after, same number of oxygens before and after. There's another concept, law of conservation of energy. It says the total energy before and after has to be the same. Although you can release energy, just take it into account. We're not going to do that. We're just going to focus on the kinds and types, or the kinds and number of atoms. So you watch that video. I'm just going to jump in right now to my technique. In my technique, I say, if you watch the video, I actually spell it out, outline it. It tells you, put a 1 in front of the most complicated molecule. Now that could be on either side of the arrow. It doesn't have to be at the end. In this situation, the most complicated molecule is at the end. And that's because hydrogen is a pure diatomic, oxygen is a pure diatomic, whereas water is actually a compound, meaning more than 1. That's more complicated. So I'm going to put a 1 there. I'm going to put a 1 there.
What does in the beginning, what does the E dot G squared stand for?
Oh, I'm sorry. It means, for example, and the 2,
Okay.
the 2 got left there from something I did. I'll show you. We're going to do it again. All right, so here we go. I put a 1. Step 1 for me, for balancing equations, is to put a 1 in front of the most complicated molecule. By most complicated, I mean it has the most elements or the biggest subscripts. And the reason why I do that is because it pins down, it anchors the most amount of information. Whereas if I put it in front of a simple molecule, I may not get that much information out of it. Notice in this situation, by putting a 1 in front of water, which is the only product, I now know everything there is to know about this reaction. How? Because I know that what I end up with is what I had to start with. And there's only 1 product. So by putting a 1 there, I have now anchored every single element and its number. I know for sure that there are only 2 hydrogens in the entire reaction, because that's what I end up with by putting the 1 there. So I come over here. This is why I call it like a ping pong game. It's like putting 1 there is like serving the ball in ping pong. Now it goes over the net, the arrow being the net, And I come over here and I pin down the hydrogen. Since I know there's 2 hydrogens at the end, there have to be 2 at the beginning. There's no other source of hydrogens. So all the hydrogens are here. And if I end up with 2 there, I have to end up with 2 here. 1 times 2 is 2. 1 times 2 is 2. So I had to have 1 times 2 here. A total of 2 here. Yay, I'm almost done. I'm 2/3 of the way done. Actually, I'm not quite 2/3. If that were nights, I would be like 5 nights, right? Yeah, 5 nights. Let's say I'm 5 nights of the way done. What I need to do here is recognize also that this 1 anchors my oxygen. So that means at the end of the reaction, there's only 1 oxygen, but I look over here and I see 2. So then I have to ask myself this very complicated calculus question. What number times 2 equals 1? What coefficient in front of oxygen would give me 1 oxygen if there's 2 of them there? What number times 2 equals 1? Algebraically speaking, that would be x times 2 equals 1. What is x equal to?
Half.
X times 2 equals 1. Yes, 1/2. Now I'm going to give you an even easier way than algebraic. Here's how I say it. Write this down. Need over half, where the half is your subscript. Look what I did. I need 1 oxygen, so I put 1 on top. That's what I need. I look at my subscript. This works. My subscript's a 2, put a 2 there, because that automatically causes that to cancel out with itself. So 1/2. And you can't have fractions in balanced equations. So what do? Genevieve, this is where I put the 2. 2 in front of this reaction multiplies times all the coefficients. So 2 times 1 is 2. 2 times 1/2 is 1. 2 times 1 is 2.